So we are still in the section on fundamental designs, which is a review of very common GLM designs that you will encounter many times in your work as a scientist and have also encountered, I think most of them in your work as an undergrad student of statistics. And last time we basically provided an overview of designs in terms of that they can lie on a continuum. And then we did a couple of things and looked at a couple of designs that we've seen previously in the course. So we looked at simple linear regression designs, one simple t-test, and multiple linear regression, not in this order because it also doesn't make sense in this order. But this is what we looked at, but we also had looked at these things before. So now it's a little bit more focused again what we're doing. So for today, the aim is to look at two things, if we manage, but I think we should. And the first thing is the independent two-sample t-test. And the second thing is one-way ANOVA. So this is what we want to do today. And remember that we are in the context of the GLM. So like the whole term, we're dealing with this equation, and we are now looking at specific forms of the design matrix and the beta parameters that then attain a specific interpretation that implement these different designs. And as example data set, for the rest of the term, we are dealing with this DLPFC volume data set that I could only, because we didn't have the handouts, briefly tell you about last time. Didn't show you the whole thing. So now you have the handout, and on the second page or third page of your handout, you see the entire data set. So it's the participants, they are linearly indexed, their age, which also increases as the participant age increases, their alcohol units that they consume, and the independent variable, the DLPFC volume. And we looked at that data already from the perspective of simple linear and multiple linear regression last time, and one simple t-test. And today we want to look at this data or these data in terms of an independent two-sample t-test and then one-way ANOVA. Good. So I assume that you have studied independent two-sample t-test and one-way ANOVA in undergrad statistics. Is there anything that you remember from that? So maybe remembering something like, when is an independent two-sample t-test appropriate, or something like that. These are typical things that one memorizes in undergrad statistics. Or when do you use one-way ANOVA and not an independent two-sample t-test? Does anyone remember that? No. Good. Which tells us something about the undergrad statistics teaching. So the fundamental situations in which you apply independent two-sample t-tests and one-way ANOVAs are the following. You have groups of experimental units, and you want to, you have at least two groups of experimental units. So you have something like group 1 and group 2. You have some values for these, so you have some data, and you want to make a statement in terms of a statistical test that these two groups in terms of if you're dealing with a two-sample t-test, are different in the sense that you can reject the null hypothesis that they have the same expectation or the same population parameter. So that's the two-sample t-test. And then the one-way ANOVA approach is the generalization to more than two groups. So if you have, for example, 3 groups, then you can use a one-way ANOVA to reject the null hypothesis that the expectation parameters of these 3 groups, or the population parameters as you called them in undergraduate statistics, I assume, are different. So that's the fundamental scenario. And we are first going to deal with the independent two-sample t-test. This always comes up, so in terms of scientific inference in the field that you are dealing with. So one-sample t-test always comes up at second-level GLM fMRI designs. So whenever you do a group study of fMRI data, you will do one-sample t-test on the second level, usually. I mean, it's the simplest thing that you can do, and usually also the easiest and best thing to do. Two-sample t-tests in what we are looking here with 2 groups, they usually come up in, for example, clinical studies where you have a control group and you have an experimental group where people have a certain disease, or in a kind of psychopharmacological intervention studies where you have, again, a control group and a group that is subjected to certain pharmacon. So in your clinical scan, have you encountered these kind of between subject group designs? Can you name an example from your clinical scan where you looked at a group design? Does anyone remember whether you looked at a group design in clinical scan? Or have you not looked into designs in the clinical scan, but only read review papers that said the brain is broken when people have schizophrenia?
Because studies comparing healthy participants to patients.
Okay.
They actually don't mention much about the designs or network.
Okay, but if you, this is the typical situation that you compare, healthy, for example, healthy control participants and participants with a disease, and then to basically validate that there is a significant, in the statistical sense, as a significant difference, one would use a two-sample t-test. Good. So now we want to apply the two-sample t-test logic to the data set that we have in our table. So this DLPFC data set, I could have left that there. And the first thing that is very helpful when dealing with designs in statistics, independent two-sample t-test, is to organize the data such that it is in line with the design. So organizing in this scenario means that, in a way you put it into a table that reflects your design, but also you adjust the notation such that it reflects the design. And in our scenario, this of course corresponds to relabeling the data that we have seen in the example data set, and we've already once reorganized that for the one-sample t-test and also for simple linear and multiple linear regression, although we don't have to do much of reorganization there. But now we want to rearrange it for a two-sample t-test. So this is in this table, I guess it's 14.5 in your script, where the data is now split into 2 groups because we want to do and study the independent two-sample or two-group t-test. It's called two-sample t-test, not two-group, but it means there are two groups. So in this table, what you see is the following. So first, there's the participant index, which is the same index as in the original data set. So this runs 1, 2, 3, up to 16. Because here the original data were split into two groups reflecting young and old age. Yeah? There would be different ways to split this data into two groups, but if we want to do a two-sample t-test, we need two groups. So I decided we look at the difference between young and old, and young being here defined as younger than, what was the age? Younger than 30. This induces then two groups. So this would be group 1 here. And here we have group 2. And here we have participants then 17, 18 to 32. And of course, what happens when we group these now according to young and old, that we throw away information that we have because we know the exact age, but now we are just saying, okay, they're either young or old, so we are categorizing them instead of looking at their age parametrically. And yeah, so we, of course, multiple linear regression design takes kind of the most information that we have, but of course, here, for tutorial reasons, we're interested in like these two groups, and we have now grouped them. Now, then it makes sense to also relabel them in a certain way, specifically the data points, and these are now these ij indices, where the first index always indexes the group, so that's 1 for all participants in group 1, and the second index indices the participant number in that group. So the first participant in that group would be 1, then 1, 2, 1, 3, down to 116. I'm here putting in a comma in the table. There's no comma. It's not important. It's maybe a little bit easier to see with the comma. In the second group, the first index is 2 for the second group. And then J runs again from 1 to the number of experimental units or participants in that group, which are also 16. And then, so this is just basically changing the indexing of the participants to reflect this two sample or two group design. And finally, the data points are also relabeled to reflect the two group design. So the original data are just put into these two columns with where we have the DLPFC volume and which is the independent variable, and they have their values as previously. So the data is of course not changed, it's just arranged in a different way. And here the data, maybe it should be J actually. That's not that nice here, because it's J there. 155, 150, and 140. Yeah, so now we have a typical situation of a two group design, for example, group 1 being control participants and group 2 being participants with a certain disease. We have indexed each participant in each group in this column as reflecting the group membership with the first index and the number of the participant with the second index. And we have then collected their data in these two columns. So for example, in terms of what you're doing in clinical scan. This could be, for example, an estimate of their activation in some brain area for the control group for 16 participants, and this then being the corresponding brain activity or bold activity in the same brain region in a diseased group of participants. Yeah, questions about this? No. Good. So then, before going into the independent two-sample t-test, a typical visualization of two-sample t-test designs is to plot the means as bars. So here we have young and old, and here we have our DLPFC volume. So you compute the mean of these values, and you compute some representation of the variability so that you can plot error bars, and then you get a bar graph like this. So this is, in my opinion, meaningful representation of such a two-group design. And then, of course, the question is the difference between the mean here and the mean here with respect to the variability in each of the groups large? That's a typical design for statistical, or a typical question for statistical reliability, or as it also called, significance. Good. So that's clear, right? So that should be fairly straightforward. Now, if you want to do a two-sample independent t-test, of course, what you can do is open your psychology statistics book or Google it and go to Wikipedia, which I actually did this morning, to look up how to do a t-test, two-sample t-test, if you have such data. Does anyone remember that by any chance? I mean, you didn't even remember what the whole situation was, so it's very unlikely that you remember the formulas. But I will write them down in a second. Need some coffee so I don't fall asleep. Because two-sample t-test is boring. So if you look up the formulas to compute a two-sample t-test, it starts like following. You have this data, and then independent two-sample t-test says you can test the null hypothesis H0 that the population parameters that gave rise to your observed data points are identical. So mu1 should be the population parameter of the first group, and mu2 the population parameter of the second group. And your null hypothesis is that these population parameters are the same. We will need that later, so I'm introducing that here. If they are the same, then of course the difference is what? Yeah. So you can also frame the null hypothesis in terms of that the difference between the population parameters is 0, and the alternative hypothesis we are interested here is only that they are not the same, which corresponds to the case that these population parameter population parameter difference is not 0. So that's the scenario that, or the question you want to investigate with a independent two-sample t-test. And to do that, you basically get a formula. So you get a t that you should compute, and sometimes this is memorized in undergrad statistics, sometimes it's not. What it says is that you should take the difference between the averages of your data points. So this y1 would be 1 over N1, which is the number of participants or experimental units in group 1. And you should average these data, so that would be taking our data points here in this group, so don't get confused about the J or the I, it's just a running index. So you take the data from the first group, compute the mean, get Y1 bar. Same thing you do for the second group. So here you have N2, which is the number of participants or experimental units in group 2. You compute the average. And then you divide this by the following: the square root of 1 over n1 plus 1 over n2 times S12. And what is S12? S12 is a measure of the variability in the data, which is defined as the following. So you compute the squared deviation in the first group from its expectation. Yeah, so these are the data points in the first group. You subtract from each one the average of these data, square them and sum them up. And to that you add the sum of the squared deviations in the second group. And you divide the whole thing by the number of data points in the first group minus 1 plus the number of data points in the second group minus 1. And then, of course, also from what we've discussed previously, you see that we here have a ratio between an effect. So the difference in the averages. So if the difference in the averages is large, then of course there's something large going on. And here you have a measure of variability. So as we discussed earlier, t-values reflect this ratio of effect versus variability, or difference versus variability. You have this t-value, and then of course you can use this the standard way of doing hypothesis testing. If your t-value is larger than some critical value, then you say, okay, this is unlikely under the null hypothesis to happen, so I reject the null hypothesis and think that the underlying population parameters are not necessarily identical. So this is kind of the cookbook approach to statistics that you should be fairly familiar with, because this is how it's taught in undergraduate statistics. And what we want to do now is to actually look at the GLM design that lies behind this approach. Yeah. So this is something that you should have learned before, and now we are going one step further to look what kind of design is actually behind that. Questions about this currently? No. Good. And looking at and providing this design behind this, for me, this was, especially also in the case of the independent two-sample t-test, quite instructive, because this is something, you can compute this, but you're not really having something in mind that generates the data. So you don't see really your explanation for the data that you cast in these formulas. You only see the explanation you use to explain the observed data when you actually look at the model. So let's look at the model now. So the fundamental idea is that data points in group 1 and group 2 are realizations of normally distributed random variables. So y1I is a realization of a normally distributed random variable, which I'm still writing in this, with a an expectation parameter mu1 and a variance sigma square, which of course corresponds to, so this is again my probabilistic versus structural viewpoint, which of course corresponds to the idea that y1 is given by the expectation parameter mu1 plus an error contribution where the error is distributed according to univariate Gaussian with zero mean and variance sigma square. So this is for the first group, and for the second group the idea is that the data points are realizations of normally distributed random variables with expectation parameter mu2, but the same variance parameter. So this corresponds to y2 I, so that's mu2 plus epsilon I, and epsilon I, well, it's the same epsilon I in fact, so we don't have to write that up again. Yeah, question?
So we assume that the variances are the same for both groups.
Exactly, yeah. So in this case, so if you're dealing with these formulas for the two sample t-tests, you assume that the variances are the same. I know there are variations, so there are variations where you don't assume the same variance, but here we do. Yeah. And it makes that fairly explicit. I mean, this from these formulas. So from these formulas, it will the same assumption that the variances are the same. Yeah, it either says for same variances use this formula, or it says this formula is only applicable if the variances are the same. Something like this. In this view, you say, okay, there is some data and this is my model. So this is my model. If you don't like my model, go away or come up with a better model. And it's very explicit. Now, the next task then, once we, like previously, have written down our probabilistic view, probabilistic view, and what I call structural view. The next question is, of course, how can we cast this in a design matrix and a beta parameter vector, and how do we have to adapt our interpretation of what we have. So we want to, of course, we always want to write such a design in terms of this equation. I mean, this is no secret. So we want to write it in this equation, but how can we organize that? How can we do that? And so I guess I'm not letting you do some guesswork today, but I just tell you. So in general, of course, our data is an n-dimensional vector, our design matrix is n times p, and our beta is p-dimensional. And of course the epsilon, I mean, this is all just the standard stuff. The epsilon is multivariate Gaussian with zero expectation and spherical covariance matrix. Now, if we want to adapt that to reflect what I've written down here, so to adapt this, what one can do is the following. So first of all, we are thinking about the data, and as data, we now have these two groups, but of course we can stack the data from the second group below the data from the first group. So we can, of course, write down a data vector as follows. So we take the first participants or experimental units data from the first group, then the second from the first group, and so on, until we are at the n1th of the first group. So this goes to n1. And then below that we put the first data point from the second group, or better, the random variable from which we conceive the first data point of the second group to be a realization. And then we stack all the second group data points below that. So we have a vector of random variables reflecting our data points, and this is n-dimensional, where n in our case here is of course n1 plus n2. Yeah. So let's do it like this. So this is now n1 plus n2. Or we could define n to be n1 plus n2, whatever. Yeah, so this is how the data is arranged. And then we want to now, again, like we did earlier when we wanted to assign the same expectation to all random variables, we now want to assign either mu1 to these data points or mu2, and this can be achieved by defining a design matrix as follows. So we take ones in a first column and zeros in a second column for the first group data, because we want to multiply this with a beta parameter vector that has mu1 and mu2 as its entries. Yeah. So if you think that you now put n1 of these 1, 0 pairs below one another, and you multiply this with the beta parameter, then of course you get 1 times mu1 plus 0 times mu2, so you get mu1. So you get mu1 for all these data points, so y1, y11, y12 until y1n1. And of course for the second group you want mu2 as expectation, and then it makes sense to use this as a design. Yeah. So that's now the design matrix. Yeah. So it has the design matrix has of course it has n columns, or n1 plus n2 rows, n1 plus n2 or n rows, and it has 2 columns because we have 2 parameters, mu1 and mu2, and of course our error contribution is simply the multivariate zero-centered Gaussian with the spherical covariance matrix, which then assigns the same variance to each of these individual points. Yeah. So this is essentially rewriting these assumptions in design matrix form. Yeah.
You're comparing the groups for only one factor, that's why the number of columns is 2. So if you were comparing the 2 groups to different factors, it would be 4.
So you mean if we go to one-way ANOVA where we have more than 2 groups? Or
not more than 2 groups, but 2 groups comparing with 2 different factors. So
what do you mean by that?
For example, you can compare, like 2 different factors. I don't know, for example, their IQ levels and their, I not a performance number that test at the same time. Can you compare it?
Yeah, I think what you're proposing, especially if you're talking about factors, we haven't really introduced this factor in level language yet. So what we have here is we have one factor in the whole design, and this factor has two levels. And if we now want more factors, then of course we are leaving the independent two-sample t-test. So because then this, if you're looking at from a factorial design perspective, this is a design with one factor, which is h, and which has two levels, young and old. So if you want to do more factors or more levels, you are not in the independent two-sample t-test anymore.
We cannot just expect the design metrics.
Oh, we will, but not in the independent two-sample t-test, because these are other designs that you're talking about. Yeah. So how are we doing with time? Okay. Now, what one can nicely do, but we will not do in all detail now, because time is a little bit short for that. What one can nicely do with the two-sample t-test design is actually to explicitly compute the beta parameter estimates and the variance estimates and the t-value, like we did all the time. So remember that the beta hat estimate is defined or equal to this, and the variance estimate is equal to this. Oh, sorry, everything's fine. Sorry, n minus p, and then we have y minus x beta hat t y minus x beta hat. So these are the definitions of, or the these are the formulas for the beta hat and the variance estimates. And then, of course, for the t-value, we've also seen that the general t-value takes the form ct beta hat minus ct beta 0 divided by the variance, and it depends on a contrast vector. And the nice thing about the two-sample independent t-test is that the design matrix is, of course, quite simple. So it's not very complex, let's say. Yeah. So it has it only has two columns. It has n rows like always, and then it has this form. So it's fairly close to the case where there's only one column of ones, like we see for the one-sample t-test. And remember, for the one-sample t-test, we then explicitly computed the beta hat estimate, or the beta estimate, sorry, the variance estimate and the t-value, and recovered the formulas for the one-sample t-test. And exactly the same thing can be done for the two-sample t-test. It can also be done for more complex designs, but then the matrices get more complex, and it's not that easy to track anymore what's happening in terms of the inversion and so on. In this case, it's fairly straightforward to track. So this is what you see there in terms of proofs of equations. I guess it's 1428 to 1430 in your handout. And it's really instructive to go over that to see how these formulas relate to the t-test formulas that you're familiar with. I will not do that in detail now. Because that will take some time. Or let's do it differently. So I will not do it for the variance and for the t-value. Where for the t-value, to get that, you also need to define the contrast vector as 1 and minus 1. Then you recover the t-value formulas, but let me at least show you how this looks for the beta hat, the beta estimate. So if one now plugs in the design matrix that we've just defined into the formula for the beta estimate, then one has to transpose it and multiply it with itself. And then invert, and then multiply the transpose of it with the data. Where the data, of course, is still in this format y1, y12, and so on to y1, n1, and then y2, 1, 2, y2, n2. Now, if one does that, what you see is here you multiply, so if we're looking at this part first, so you multiply n1 once and add them up, so you get n1. So you have n1, and then you're multiplying n1 once with zeros and zeros with ones, so it is also should be a 1, of course. So you get 0. Here you're multiplying zeros with ones and ones with zeros, so you again get 0. And then for the final you multiply zeros with zeros, but then n2 ones with and 2 ones, and you add them up, so you get this. Here you are again summing up the data points in each group, so these ones and these zeros, so these ones collect all the data points in the first group and sum over them. The zeros leave the second data group data points untouched, so you get y1i, so you get the sum there, and of course the same for here, so where you have the zeros, you leave out the data points from the first group and then add up the data points in the second group, I, 1, 2, and 2. And here, of course, you still need to invert this matrix. So what's the inverse of this diagonal matrix? Exactly. Because if you multiply this matrix that you see there with the matrix n1, 0, 0, 1, and 2, you multiply this with the n1 and 2 matrix, then of course you get the identity matrix, 2 by 2 identity matrix, and then if you multiply these then you get as estimates for your expectation parameters. So remember that the beta vector encoded the population parameters. So these estimates for them are then 1 over n1 times y1i, so the average of the first group, and 1 over n2 times yi, so the average of the second group. Yeah, and exactly the same can be played out with the variance estimate, as you see there in 1432, which then essentially recovers the formula for this S12, except for oh, maybe I forgot. No, I see that what I forgot here was actually a square root, because if this otherwise it would need to be square. So this the variance estimate recovers this formula here, or the square better, so the square of it. And then if you plug in these and the contrast vector, where are we here? this contrast vector into the T formula, you get the T statistic value. Yeah. So I would really recommend to go over these details because you practice your matrix algebra skills and you get also more of a feel of, again, how the general theory of the GLM that we covered most of the term relates to these specific applications in terms of specific designs. Yeah, so I highly recommend to do that. But you have to do a poster, of course, which is something. Good. Questions about this? No. Good. So now what you should have seen from this, what you should get from this is that behind these formulas that you learned for t-tests, or at least you heard for t-tests, there is a model, and this model is of course the GLM. That's not too surprising. And you can then view computing t-statistics as doing some statistics and parameter inference, essentially, given an underlying model which you now have explicitly defined. So you actually see the model that's behind it, and you realize that all statistics is model based, and that there is no objectivity. And that's something. Jesus. Good. Then let's take a break and continue after the break with one-way ANOVA.